All right, last big day. Tomorrow's the final day for the interview, so hopefully we can get a lot more done today to prep for tomorrow. All right, we've got about 30 seconds left here before the session starts up. Let me check my audio levels. Everything looks to be balanced. Good, good, good. Okay. Starting off to be a good day. Got my 8 hours of sleep, ready to do some Microsoft Focus questions. Probably going to be live for, going to aim for 2 hours today. Hopefully. Yeah. This quarter's thankfully been treating me nicely. I've had a lot more time to put towards practicing. Okay. So let's see, hash table. Implement a hash table with the following methods. Construct a new instance of a hash table. Okay, easy. The most difficult thing here is going to be to come up with a hashing function. We're going to use a standardized array. See, the way to do it is going to be very dumb. Let's see. We're just putting in integers into our hash table. So we're going to do ints. It's going to be int array of a called table, and in the constructor we're going to instantiate this array to be. The most difficult thing is going to be dealing with collisions. There's many ways that you can deal with collisions when building out hash tables. You can use buckets at the end. You can use lists at the end. You can do whatever you really want, but the best plan for dealing with collisions is to just not have them. So you want to build out a hashing function that allows you to avoid as many collisions as possible. So let's try and build out that hashing function. Right, we're gonna do table equals new int of size. Let's say size 100,000. This should automatically avoid collisions. What we're gonna do then is to say we need a way to let's set it to 0, I guess, if it's not. Let's call it 0 an empty bucket in the hash table. So what we're gonna do is say then that table at let's make a hashed key. We're gonna make a hash function, private int hash. We're gonna pass in a key and we're gonna return a value. So first of all, we're gonna do this. Oh man. Okay, we're gonna return key mod. We're gonna return key mod table.length. This is a very, very simple hashing function, just keeping the key in the place. Seems like my laptop's running out of bandwidth to run this adapter because my mouse is lagging all over the place. Okay, we're gonna do table at hash, let's say equals 0. Then we're going to do return table at hash. And then for put, we're gonna do table at hash is equal to val. And that's our hash table, really. That's the hash table. It's very easy. I gotta actually hash the key. There you go. So let's go ahead and hash our key. And after hashing the key, we only have to change our hashing function in one place to get this to work. Let's do a -1 for removal. My result. I guess we can pre-fill the array with -1s. Use JS array. 0 I is less than table.length. Table at I is equal to -1. Pre-filling it is going to be the most expensive part of this operation. How is that not a statement? Oh, there you go. Gonna use this question as a warm-up question to wake up, hopefully. Yeah, with a very, very slow hashing function. Let's change this up and see how... Try 10,000. Can we get over 10,000? Yeah, it's gonna be a matter of finding the right size for this table is all it is. Yeah, I don't know. Let's do 50k. Because 100k guarantees that we can fit everything, 50k might not. Just depends on their test cases. Ooh. Alright, let's move on to the next question. We solved this one, not the quickest, but maximize social distancing. Ooh, love this question. Okay. You were given a list of integers seats containing ones and zeros. Each element seats represents a seat in either that is either occupied or empty. Given at least one empty seat and at least one occupied seat, return the maximum distance from any empty seat to the closest occupied seat. So, the way that we tackle this question is actually quite interesting. We are going to do a couple things, right? We're going to do a left to right scan till first occupied. Then we're going to do our R2 left scan till first occupied. Afterwards, we're going to start at first occupied until last occupied. And this one, divide distance over 2. So we're going to scan from both edges and then scan from the middle. So this is going to, let's say, looking at this example, I'm going to start from here. It's going to give us a distance of 3. And then we can keep going here. 0, 1, 2, 3. Okay, let's try that. So int first occ equals 0, int last occ equals 0. I'll set these both to actually -1s to see if we only have one occupied. Okay. We're going to go ahead and do that, and we're going to do, let's do the RTL first, or left to right. Screw it, I'm not doing right to left first. So for int I equals 0, I is less than seats.length I plus plus. Cool. We're going to go ahead and say if nums seats, not nums, seats at I is equal to a 1, meaning it's occupied. First occ is equal to I, and we're going to break out this loop because we don't need to keep looking further. Then we're going to do the RTL. And we're going to go from the right side and do the same thing. So let's set this to seats.length -1. I is greater than or equal to 0. Subtract from I. Perfect. Okay. So by doing this, we're going to set last occurrence and then we need to go between first and last. I do have a pretty cool project to show off kind of after this session ends, so I'm kind of excited for that. It's a project we've been working on in one of our courses as a team. Honestly, so far, quite proud of it. Okay, so between first and last, so for int I equals first occ I less than last occ I plus plus. Let's do cur start per end. Equals 0. End equals -1. Int max dist is equal to -1 as well. Cool. So we're gonna say is int curdist as well equals 0. So I actually don't think we need to keep track of that. Okay, so we're gonna say if seed set I is equal to a 1, a couple things need to happen. We need to check for updated distance. And then update counts. So we're gonna do int, so max dist is equal to the maximum of itself, as always, compared to curdist over 2. So if we have 3, 3 over 2 is 1.5, which should be 1. Okay, I think that's gonna be, and then update counts, so curdist equals 0. Otherwise, 0, we just increment curdist by 1. We don't actually need to keep track of the current start and end because we don't really need to return that ever. So I think all we should be having to do at the end here is to say return math.max of max dist math.max. I wish there was a max function in Java that allowed you to have an arbitrary number of parameters. Would just be great. Okay, math.max of first awk minus 1. So pretty much saying if we encounter the first one here, we can we have a distance of this many seeds. If we encounter the first one here, we have a distance of 1, 2, 3. So 0, 1, 2, and 3. Actually, I don't think we need the minus 1. I don't think we need that. And the next part is to say seeds.length minus last awk. So then if our last occurrence was here, we're doing 0, 1, 2, 3, 4, 5, 6, 7, minus 0, 1, 2, which is 5, 1, 2, 3, 4. This is the one that needs a minus 1. And I think that should do it. Let's try it. Compile errors everywhere, all over the place. Okay. Goodness. First. Okay, that's the wrong answer. That is A-okay. Okay. Let's do this real quick. Right here, let's do a println. I hate these easy problems because they require a lot more, like, just thinking instead of utilizing data structures like the more difficult ones. LTR plus first awk println RTL plus seats.length minus 1 minus last awk. So these should in this case both be 0. Gotta make sure to have our parentheses in these strings because we can't concatenate strings and integers. So yeah, those should both be 0 because that makes sense. So, the next thing to do is to say, let's do this. curdist. And we're going to print out the cur distance. Curdist over 2. We should be hitting 1, 2, and 3. So we should be seeing curdist print out 3 at some point. If we don't, we have an issue. Oh, I see what the issue is here. Yeah, we can do less than or equal to. Why did I capitalize this curdist of all things? Nothing else is capitalized. Yeah, there's 3. Divided gives me 1. Do I need to, like, spend a few eternities since you streamed, if I remember correctly? I streamed yesterday. I haven't been gone for all too long. I've been doing Microsoft interview prep. I did take the weekend off, though. It was a much-needed time off. Yeah, I don't know, maybe the notification didn't go through, but yeah. Yeah, it was live yesterday. Okay. I guess it's just a matter of, like, this integer division not working correctly. Weird, okay. Okay, so int result equals 0 if curdist mod 2 equals 0, result equals curdist over 2. Otherwise, we're going to say result equals curdist over 2 plus 1 because it's odd. Then we're going to do our math.max statement with the result variable now instead of curdist. That should do it. Yeah. Super slow because of this println right here and the println up top, but we're gonna get rid of these. Alright, let's hope that that fixes it. Let's see if that's faster. Still technically, oh man, we're only hitting every element in the array once, so yeah, okay, cool. Let's go to the next one. Ooh, number of islands. Given a two-dimensional matrix of 1s and 0s, return the number of islands in the matrix. A 1 represents land and a 0 represents water. So an island is a group of ones that are whose neighboring perimeter is surrounded by water. Neighbors can only be directly horizontal, vertical, and diagonal. I love this question. Okay, this question is a very, very, very fun question. I remember this being my first graph problem that I ever solved. So, the way that you approach this is very interesting. You modify the matrix in place. So what we're going to do is we're going to iterate through every spot in matrix. If we encounter a 1, up count plus 1, then do a BFS to clear every 1 in that island. Boom. And what that does is it allows us to, every time we find an island, like for example here, we find it, we pass it along to the BFS, we remove it, and we're done. Here, we go, we find this one, we find this one. We pass this in, it'll recursively remove this whole island, and that just allows us to take care of this problem easy peasy. So, let's go ahead and do that. I equals 0, I is less than I plus plus. Let's do that. Cool. Man, setting up nested loops has become just like a thing I can do in my sleep at this point. J0 matrix at I dot length. Gotta love O of one axis times n arrays. Okay. Let's hope. Nope. Okay. This thing decides it wants to jump into performance mode every time I unplug it. I'm gonna go ahead and put you back into silent mode. I am literally just on a website. Okay, so we're gonna say if, we need to keep track of our account. If nums at I j is equal to a 1, add and remove. So we're going to do islands plus plus, BFS on matrix, IJ. Cool. Let's go ahead and write up this BFS method. Public void BFS. I love the idea that these are passed in by reference, so you can just modify them easily. Matrix, int I, int j. I think what we can do here, let's pass up an int, just so I can return out of these easier. Okay. So what we're going to do here is to go ahead and, first of all, if I less than 0 or j less than 0 or I is greater than matrix dot length minus 1 or j is greater than matrix at 0 dot length minus 1. Out of bounds, we're going to do, we're going to return -1. Easy. Okay. Then, matrix I, so, how do we actually, hold on. We just need to go left, right, up, and down here. Nothing special. Okay, if matrix I j is equal to 1, return, we're going to set matrix I j to be equal to a 0, and we're going to always do a BFS in all directions. So we're going to do BFS on matrix of I plus 1, j. I'm going to do this 4 times. Minus 1. And we're going to do the same thing, but with j. And we don't really need to consider the bounding conditions because we already took care of that at the top of the method. There we go. And up here, I think if we just return our islands count here, we should be good to go. Okay. Stack Overflow. Oh, right. We probably need to move this into here, because we only want to do a BFS if we still found a 1. Index 2 out of bounds for 2. I need to stop replacing this J with an I. Sweet. Nice. Done. Okay. That's easy. Great question. Very great introduction to graphs. It's a good refresher. I'm glad I got the chance to do it. Okay. Interleaved linked list. Given two linked lists, return two linked lists interleaved starting with L0. If there are leftover nodes, they should be added to the end. Okay. This one is also not too challenging. If my questions tomorrow at Microsoft are like these questions here, easily gonna get through them. But knowing my luck, there are going to be some stupid difficult like DFS, BFS. Okay, wait. So we're starting with L0. So let's do this, right? Let's do LL node head equals new LL node. And we're going to do LL node temp. It's going to point to head. So while L0 does not equal null, while they're both not null, because we'll take care of the excess after, right? Okay, so we're going to say temp.next is equal to L0, temp.next.next equals L1. And we're going to move them all along the appropriate amount. So L0 equals... Man, if they ask me how to reverse a linked list, I'm actually going to fail this interview. I can never remember how to do it like in O of 1 space. Doing it with a stack is fairly easy, but... So, temp equals temp.next.next. Then L0 equals L0.next. L1 equals L1.next. And right here, before we take care of the excess, first of all, let's set up like an actual, correctly set up while loop here. Then we're going to go down here, and first of all, just return head.next. And this should work for this base one. Still does not compile, huh? Right. Temp is a reference to head. My result is 712. Weird. Is it... Wait, what? Why? Okay. Shouldn't work either. Yeah, 7-1. Why doesn't that... Hold on. Okay, now I'm a little bit confused here. No, this definitely needs to be .next. Strange. Okay. So we have our temp.next is equal to L0. I think I can see where a bit more of the difficulty comes in this question. Because the next of 1 points to 2. So doing temp.next.next brings us to 2 and drops off the 8 and makes L0 null, I think. I guess we can hold a an L1 temp and an L2 temp. Equals L1. L1 equals L1.next. L1 temp.next equals null. We can do the same thing for the other one. To get rid of that connection. Let's do L. L0 equals L0, L0 equals L0 dot next to move it along. And update the next for this temp. L0 temp, L1 temp. Then I don't think we actually need to move these along any further because we're already taking care of that. Does not compile. L1 temp. Okay, please work. Still wrong answer, we got 8 and 2. Helps to move this one along, actually. Cool. Let's try it. It's not gonna work because, yeah. Okay, so if L1 is not equal null, temp.next is equal to L1. If L2 is not equal null, temp.next equals L. There's no L2, there's only L0 and L1. That should take care of any sort of, yeah, there we go, easy. Okay. Cool, that was a pretty nice set of questions. Okay, so we got 18 minutes left. Let's pull up a LeetCode tab. Might as well while we're at it. LeetCode. I'm gonna try and do maybe one high-rank Microsoft problem and then come back to do another session of binary search. I think generally the thing that I find more helpful, I'm very good at deducing like very problem-specific things. For example, you know, if I know the general algorithm, I can pretty confidently change it up to follow a specific problem guideline, but I can't really bank on like, okay, I've seen this problem before, so I can solve it. For me, it's a lot more, I guess, feasible to work on sort of the general algorithms and then apply them to problems. Like, it's never really been a big help to like, okay, I'm gonna study these problems and hope that these problems are the ones that show up. Just not the way that it works for me, I think. Okay, I don't know if I even want to sort it by like frequency or it's just like, yeah, I've saw, okay. Median of two sorted arrays is, my thing, right, what I'm assuming here is, from what I've heard, Microsoft interviews are easier than Google. And I did quite well on Google, I'd like to think. I mean, I did pretty okay. So I'm going to just bank on the fact that it's going to be easier. I'm also going to just bank on the fact that if I see a hard problem, I'm going to fail it regardless. So there makes no sense to spend my time practicing hard problems. I've heard they're pretty much all easy, medium, so longest happy string was a very interesting one to look at. Reverse words in a string. Guess let's try this one. How's this looking? Given an input string S, reverse the order of the words. A word is defined by a sequence of non-space characters. The words are separated by at least one space. Return a string of words in reverse order concatenated by a single space. Note that S may contain leading or trailing spaces or multiple spaces between two words. The returned string should only have single space. Do not include any extra spaces. Okay. Were there no hard problems on your Google interview? Hey, yeah, it's good to see you, Trial. I think honestly, there might have been, but not having the hard tag by them might have made it a bit different. I think my graph-based question might have been hard. I can't really, go into depth about what it was because they make you sign like an NDA that you won't talk about their questions. But I believe the graph problem might have been hard, and genuinely that was like the only one I struggled on. I mean, not to say the rest were easy. I think it was pretty much hard, 2 mediums, and an easy. The last one, thankfully, was easy because at that point I'd been through a behavioral and 4 45-minute technical, or 3 45-minute technicals, So what I want to do is split this into a string array. Strings equals s.split, and we're going to split it at a space character. Cool. First of all, let's do for int I equals 0, less than. I want to do actually strings.length. -1, greater than or equal to 0, I minus. Let's print these out first. Println strings at I. Hated this problem. Well, okay. Go on. I want to hear why you hated it. Like, what about this problem was annoying? I mean, the fact that there's like leading and trailing spaces is fairly frustrating, but it's nothing that you can't handle by utilizing this method. Granted, I don't know how it's going to handle like 10 spaces. If it just... I guess you can traverse it backwards, and every time you encounter a character, you keep going until you encounter another space, then reverse that string and attach it to your string builder. But I want to try this one first. And just see what this gives us. That's S. So return S. Blue is sky the. Huh. Okay. Hold on. Okay. So here's what we're going to do in your string builder. It's so finicky, so many edge cases in my opinion. It's the kind of problem I probably wouldn't be able to get right without running the code multiple times. Yeah, it's kind of seems like it's going to end up being that way. Let's real quick, string builder. I mean, I hate problems where it's like, okay, you got the algorithm, you got the general idea. What if there's this like one weird case where like your algorithm just doesn't work? And then you have to spend like, you spend 15 minutes actually coding the problem and then 30 minutes trying to solve that stupid edge case. I don't know, I feel like that shouldn't really be taken into consideration as much as the general ability to solve that algorithm. If strings at I, get this, dot length is created. Wait, too much JS. Too much working with JS objects. Strings at I dot length is greater than 0. What we're gonna do? The s dot add append. We're gonna append, what are we gonna append? We're gonna append strings I plus a space, right? Now I might be wondering, how do we get rid of that space? Get this. We do ds dot substring dot, turn ds dot to string. From that, we're gonna take a substring from 0 to the to s dot. It's gonna be length, isn't it? The s dot length -1, is it? Yeah, there should not be a semicolon there. String boulder. Okay. Ha, nice. Okay, let's submit it. Nice. Terribly slow, terribly inefficient, but it works. Goodness, yeah, that's a terribly slow solution. Okay, yeah. Send in the one that you were thinking of, because I'm curious to see that one. Alright, so there's 10 minutes left here. So I guess from this, first of all, let's remove this println. That's going to be one thing that slows it down considerably. Ooh, yeah, no, we've upped that runtime significantly. But the faster way still to do it, I don't want to implement it, but I'll write it out here. The fastest way to do it is to start at I-1, start at end, go until you find a car, a letter, start counting, start appending to string, to separate string. When you find space, append reversed separate string to string builder plus space. I don't know how to mix these two up. Okay, I'll take a look at that in a second here. And then what this will allow us to do, for example, is to go through it. We find the E, E-U-L-B, and then we append this reversed to blue onto string builder, so we get blue and a space. And that'll just running this algorithm allows us to do it in O(n) time, avoiding having to do the whole split shenanigans and that. Alright, let's see the problem. Text justification. I think I might have heard about this one. Ooh, it's a hard. Okay. Given an array of strings words with a max width, format the text such that each line has exactly max width characters and is fully left and right justified. What? Wait, hold on. What? Okay. I guess the what? Okay, because you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I'm so confused. Okay, wait. Yeah, I'm not gonna tackle this one today. I mean, I have a general idea of how to do it, but because I'm assuming you need to add a space in between, so you might want to, if you have to do it in order, probably like, I can see why there'd be a ton of edge cases here, but you want to basically count your characters plus count the word length plus a space, word length plus a space until you get up to the max width, which is I think the easy part because that allows you to greedily pack as many of them as you can into that row. And then you need to figure out how long it is, figure out how many extra spaces you have, and add in those spaces in between those words evenly. Which sounds like something I genuinely don't want to do right now, but I will keep this question as like here. I'll add it to how do I like easy or hards. Done. It's one of those things where like the idea behind the question itself isn't particularly challenging, but implementing it is just like difficult. Acknowledgement. Yeah. Because the last line must be left justified, because instead of fully justified, the fact that this last line is left justified instead of fully justified is just kind of annoying. The justification is what makes this question annoying, figuring out where spaces should go. How's this one looking? Okay, so I guess these 5 minutes, I do want to show. Um, I want to show off this cool project we're working on. So one of the courses that we have at the moment is a game development course where basically you're provided like a very basic framework of a JavaScript game engine, which just does like ticks. It does just has like a basic update and draw loop, and what's it called? Hold on. Basically building just on top of that, and we decided we're gonna make a rip-off clone of Mega Man X4, but call it our own thing. So this is pretty interesting because it's all done using just that framework and everything that we've built on top of it. So these sprite sheets, we updated the animator that we were given to work with our sprites, all the logic for these enemies, all of the movement code, all the collision code, pretty much all the physics code as well, like everything that, aside from having the ability to draw things onto the screen and have a update loop that hits every entity in the game once, was pretty much done from scratch. So we have a couple basic things implemented at the moment. There's no attacking animation because we haven't gotten around to that, but you have this little Goomba-like enemy walking around whose whole thing is that he waddles around. Every once in a while will sit down in his shell and becomes invincible for that time. Very proud of that one. Made that one myself. There's this ground hazard, which currently is, I think, shoved too far into the ground, but you have your player with a run animation, a jump animation, got the nice little background parallax going. I think that we fixed the collision, because before this it was just like a lot of teleporting. That's a weird graphical error, wasn't there last time. But yeah, it's a very simple stage game prototype for now. A couple cool mechanics though that some of our group mates have implemented. Might need to resolve how we set the speed to 0 when he hits the top, because you can just do a little bit of a Minecraft ice jumping, but you can make your jumps, you can really do whatever it is that you want to do. If you grab onto a wall, you can sort of slide down it, do a bit of a wall hang, and then you can go ahead and also jump from the wall and sort of do a bit of a climb. It's a little bit finicky still, but still very proud of the state of this project. We're doing a demo of it today in its current state. There you go. But yeah, I pretty much made this level generation system from scratch. It's a pretty interesting topic, and so far, you know, I've learned quite a bit regarding how to build out things that feel kind of good to control. Thank you, appreciate it. A little bit of graphical bugs here and there, but it's okay. Honestly, quite nice. It's definitely a nice break and a big time sink because there's just so much to do. Another cool feature, I guess, is like we recently implemented a general debug menu to where you can turn on the debug for the collisions for pretty much everything, and you can see where the colliding boxes are for all of the entities, for all of the pretty much everything. And I haven't actually seen this debug menu before. This wasn't my part to implement, but overall, yeah, gonna keep updating on progress as we go along. We got another, what, 6 weeks to finish this? But yeah, overall, pretty cool, pretty fun, quite enjoyable to work on. Alright, how are we doing here? All I did was keep track of a head node. The hard part is to shuffle around and a temp. Okay, maybe it wasn't in place. Alright, so let's go back to our Microsoft list here. Okay. Let me back to problems. Problems, let's do Microsoft. I'll go ahead and start up another session. Okay. And I'm going to start up another session, do another... Okay, how's the scoreboard looking? Oh wow, that's how fast was my solution here? It was like what, 70%-ish? Yeah. Cool. I guess in this time we can go over and look at the time and space complexity of these previous solutions. Data structure problems, not sure how to really do time and space complexity. So for this one, I know that the time complexity of each of these methods is O of 1 because we're just hashing the key and indexing an array which is O of 1. Not the most space efficient thing, we're just using a terrible, terrible hashing function. This should never be the hashing function that you use. I remember spending a couple hours trying to design a good hashing function for our data structures course, and it seems like so long ago now. 3 a.m., couple cups of coffee into the night. Good times, good times. So maximizing social distancing. This question was definitely interesting, I think, the first time I saw it, because I don't know if you can do it with like a general one pass through. Maybe you can, but it seems like there's a lot of edge casing and stuff to take care of. So I said, screw that, we're not doing that. Still considered O of n because we only really hit every element once. But what we're doing is we're starting from the left, going up to the first one, and thinking, okay, if I place myself the very, very left edge, how far can I go before I actually hit the first one? Then we do the same thing starting from the right edge. So we're going from the right in as far left as we can until we hit the first one. And the thing is about that, the reason that we want to do it that way is because calculating distance from the edge to the first one is not the same as calculating this distance, because this needs to be divided by 2. Then we want to start at the first one and go up until the last one, and basically check if we have a 1, then we need to calculate how far we've been able to come. If we have a 0, we can just increment our current distance plus 1. Otherwise, this is a little bit of dumb math, because I could do like floating point division and then take it ceiling to avoid this if statement, because we just need to divide by 2, and because integer division is always floored, we just need to change that. And then we return the max of whatever those 3 were. Easy, O of n time O of 1 space. Moving on, we have number of islands. Number of islands is a very, very interesting question. It was, again, my first graph problem that I ever properly solved. I think time complexity-wise, this is... I think it's n squared plus, like, n squared, maybe, at the worst, because we are iterating... I guess it's just n. Wait, hold on. So, if... that's a good question. Is doing nested loops considered n squared or n? Because I mean, I think it's just n, really. And then this whole thing, recursive runtimes is not my strong suit. So because at the worst, right, if every element in this is a 1, this one would go through everything. I think n times m, okay. I think then this is, well, they define n and m as width and height of the matrix, so this would be n times m. Okay, so yeah, that makes sense. My only question to that, right, is how does this chunk fit in? Because let's say here we are at n times m, n times m. But after the BFS matrix search, the BFS could hit all n times m elements. So is this BFS runtime then like also n times m? N times m at the worst. Because at the worst, it will hit all those n times m elements. Which makes me think this is n times m, n times m, which is not a fun runtime. I guess the reasoning behind this being 100 is that this may well be, what, like, n squared times m squared, which is about n to the fourth. That's my best guess at this, honestly. My best guess here is n to the fourth. Space complexity, it's O of 1. We're working with that same matrix, only making constant variables. So my best guess here to say is it's about n to the fourth or n squared times m squared, because the BFS at the worst could run through it. And this outer loop has no knowledge if there are or are not any more ones in it, so it still has to check everything. Great. So interleaved linked list. Cool. That's not correct because you won't visit anything twice in your matrix. Interesting, because my logic here, right, was that this could visit, you could technically visit everything twice in your matrix. Let's say we're given a matrix that looks like this, right? We have 1, 1, 1, 1, and we have this same matrix here, like that. If we start here, we'll find this. We will pass this along to our BFS. The BFS then inherently will visit every single one of these, and then afterwards, this nested loop will once again visit every single one of these. Actually, no, because... But it will be set to 0. I guess, yeah. So maybe just n times m. Yeah, that makes more sense. Cool. So the first loop is n times m and then O of 1. Yeah, and I guess that we're looking for the average sort of runtime. I guess, yeah, it's very difficult with recursive functions like this. Okay, interleaved linked lists. Quite literally, all I did was just keep track of a head node, sever off these things, add them one after another, add top at bottom, add top at bottom. Once one of them is null, if either one of them isn't null, we just shove it onto the end and we're good. I think technically this is done in O of n time, O of n space, because the O of n space comes from these temporary linked lists, because I couldn't lose track of where it would be. N plus 1 times n plus 1, which is n 10. Yeah. You gotta remember that constants and stuff just kind of go away when you think of the general term. So, like, obviously, 5n is faster than 200n, but in the end, they're still both O of n. So yeah, this one, not terrible. Should I add a hint to it? I don't know. Okay, let's get ahead and ready up for this next set. While this question's readying up, I am gonna step out and then be back to start this next session. Okay, let's see what we got. Oh boy. Return max power if you could if you bind this on. I think I solved this one yesterday, did I not? Okay. Beer bottles. You are given an integer n, representing n full beer bottles. Given that you can exchange 3 empty beer bottles for 2 full beer bottles, return the number of beer bottles you can drink. Return the max buff you can. Oh, wait. This one, easy. This is just once. The one I did yesterday was just like buy, sell, buy, sell. I guess the... Yeah, this one's easy. Hold on. Yeah, that one was challenging. Okay. Still don't want to do Wolf of Wall Street, though. It's wolf and wolves, plural. Okay, so. I guess while n greater than or equal to 3. We can keep doing this. This is just a math question. I don't like math questions. Okay, it's been a while since I've done any sort of math. It's all been like CS and like super CS focused math. Okay, so we can exchange so int exchanged equals n over 3. So int drank equals 0, right? So we're gonna drink all n bottles at every stage. So drank plus equals n. Then we're gonna do exchanged of n over 3. So we want n to decrease by 3, and then we're gonna do. Can I not just do like n equals n over 3? Oh wow, let's go, more people. N equals n over 3. Let's do that and return drink. Drink plus n. Yeah, I was gonna say there's no way that works. It's way too easy. Goodness, I really don't want to do this like math question. How close was I? Alright, let's just do this one. Let's do Wolf of Wall Street, might as well. So, what we want to do is do one traversal where we I guess find the min and then the, I mean we do need to just find the min and the max. Let's do it in n squared first of all, and then we'll go from there. Int min equals integer prices at I hash 2 integer dot max value int max equals integer dot min value. Cool. What we're going to do after this is just to say for int I equals 0, I is less than prices dot length plus. Forgot to keep track of the actual int max profit. don't actually need to keep track of that. Okay, so we're gonna do a second loop. J is gonna be equal to I plus 1. Less than prices dot length. Finally increment J this time instead of I. And then we're gonna say max profit equals the maximum of profit and nums at J minus nums at I. Very bad solution. Goodness, Archit, where did you, how did you even, it's prices. Yeah, very bad, very slow, but
That's the main thing, you see. I think that's why the awards have changed.
No way.
The kids
It's TLEs. Oh, they're smart. They aren't gonna let me just cheese my way through it. Come on, let me cheese through it. Just give me a 0.1% here. Okay. So. I guess the logic here is to find can we be greedy? Can we? Because the max profit here is from here to here. I guess we can maybe use two arrays where we here's what we're gonna do. We're going to do it's gonna be very space intensive. Int mins equals new int of prices dot length, and we're gonna do the same for maxes. We're gonna do maxes for int I equals 0, I is less than prices dot length plus plus. This is, I think, even worse actually. Let's see. Int min equals prices at 0. Int max equals prices at prices dot length minus 1. Actually, I guess no, this is technically faster. It's O of n instead of n squared.
The kids are changing
Okay.
for a start, and so is the music changing.
Jeez, okay. What we're gonna do now is to say if prices at I is less than min equals prices at I. And we're going to update to set mins equals min. We're going to do the same thing for our maxes. But starting from the end this time. There we go. Gren equal to 0. I minus minus is greater than max. The max there is prices at I. Maxes equals max. Then we're going to iterate through both arrays. Actually, we can just do the calculation inherently in this one. We don't really have to go further. Let's keep track of This needs to be indented by 1. Okay, so max profit 0. So if max profit is equal to max profit is equal to math dot max of max profit maxes at I minus mins at I. Mins at I equals mins, and so does maxes at I. There we go. Cool, faster. Still no, huh? What are we expected to return here? Edge cases, edge cases, edge cases. Okay. Beer bottles is just like an algorithm that I can't figure out, so we're gonna skip beer bottles for now because I'm just banking on it not showing up. Okay, what do we got? Largest tree sum path. Given, return the largest sum of any path between 2 nodes. Ooh. Okay, this one's gonna be challenging for sure. Largest path sum is 8 to 7 to 4 to 12. I think this one might be easier than I'm thinking it to be, because all we're doing is using a post-order traversal at every level, count C left and right sum. If it is bigger than previous max, we then need to just update it. Because yeah, so let's say we're looking at this here. We do this here. From this whole branch, the biggest sum up is 15 here. And then from this branch, the biggest sum up would be 12. We add those together plus the 4, and that's that. Not too terrible. Lowest common ancestor. Given a binary tree root in integers a and b, find the lowest value node that has a and b as descendants. A node can be a descendant to itself. This one I think is going to be the actually challenging one, because we need to somehow do checks for a and b in descendants. Checking for 1, easy. Checking for 2, not so easy. Okay, so how do we... How do we actually tackle this? Okay, so... Ooh, there goes my mouse again. Please stop lagging. Okay. For this one, I think I'm gonna use gonna cheat a little bit and use like a global method. Max equals 0, public int helper tree root. So we're gonna pass this along to helper root return max. So first things first, if node, let's call this node, it's just easier to work with node. If node dot left, if node is equal to null itself, if the node itself is equal to null, we can just return 0. Otherwise, left and right for their sum. Never seen. Just start. I love the profile picture. Okay. So traverse left and right. So int left. Okay, int left is equal to helper node dot left. Int right equals helper node dot right. I don't know how I managed to like right align this, but there we go. Cool. So what we need to do now is to say max equals math.max of max versus node.val plus left plus right. And we're going to pass up return node.val plus left plus right. And this should allow us to, at every node, have the sum for all of its branches. Ooh. Might have done something wrong here. Are we stuck in an infinite loop somewhere? Or is it just being slow? Might be that it's just being slow. Cool. Submission timed out, but why would it? Why? Why do you time out? I don't even think that's on me. I think that's just the servers. Yeah, I can't submit. It's not giving me a TLE or a Stack Overflow or anything. Is binary search kicking me off? Jeez, okay. Here's what I'll do. I'll set up the Be Right Back screen so I don't have to stream this because it kills my internet connection. And I'm just going to refresh the page and hope I can load back in. Okay. Please work. Cool. Wrong answer. I'm okay with that. Wrong answer is 35. Oh, wait a minute, yeah. Okay, yeah. We need the max from left to right. And I think that should do that for us. Because we only need the max path. We don't want to sum up all of this. We only want the bigger of the two paths. Still no, huh? 19, okay. Let's see, let's do... println, checking, node.val, left sum, println, we're going to check the left sum, and then the right sum. Just gotta make sure that the sums are coming out right, because if they're not, then we have to reevaluate a lot more of this. Okay, so we are checking 5, left, right, 0, checking 2, left, right, 0, checking 4, left, 2, right, 0, checking 8, I want to see checking 7. Left is 6, right is 8. We're checking 12. Yep. Checking 4. We get 7 plus 7 is 14 plus 15 and 12. Ooh, okay, wait. This right here, this one I think needs to be just left, right. Because we want the biggest path we can get down there. We don't just want to stop at 4. There we go. It's a lot of tracing with these trees and figuring out what your algorithm is doing. Dang it, okay. Yeah, edge cases. Okay. Between any two nodes. This is a dumb question because 5 and 5 are not two nodes. I stand by that. This is dumb. It should be 3 at least. Yeah, 5 is not... Why can 5 have a path to itself? You know what? You know what? Fine. You want to be that way? I'll be that way too. Okay. Root.val max. There you go. You happy now? Cool, I guess you are. If it's gonna throw these dumb edge cases at me, I'm just going to get rid of them. Because a path to 5 from 5 to 5 is not a path between two nodes. Sweet, okay, let's go ahead and work on this last one. So, in integers AB, find the lowest node that has A and B as descendants. Okay. I think we would just need to pass up a Boolean value of if A and B were found somewhere in there. Oh, I have a really dumb solution to it, but really, really dumb solution. It's very slow. Is it? Yeah, it's all the big companies for this one. My best guess, because I don't know how to do multi-value searches in a BST at the same time, so I think my biggest guess here would be to do from every node, like have two helper methods called like found left and found right, and wait, so find the lowest value, looking for a 3 and a 5, that would be a, find the lowest value of the lowest node, lowest I'm assuming in terms of depth in the BST. So what if we were to have like a has A and has B search? Let's do public Boolean search tree root node and then int target. I'm gonna just write a method to search through the tree. If node equals null, right away we return false. Search left and right trees. Assert Boolean left actually one thing we're gonna do right away, right, to say if we do want to do this as a top-down search though, because we want the lowest node, and if something's lower we can always update it. Okay, so if node.val is equal to target, we return true always. Then Boolean left equals search.left, not search.left, search node.left target. Cool. And then I'm gonna do right. And from here we're going to do a return left or right. So what this will allow us to do is basically search from any given node for okay, this function will allow us to find a given value in a binary tree's subtree, right? So first of all, let's do this, right? First of all, return a -1 for now, just for ease's sake. Let's do search if search root A we're going to print out that we found it. Plus A. Cool. Just making sure. Found 3. Sweet. Okay. Okay, int result equals -1. Here we're going to return result. And we're going to do if search root A and search root B result is going to be equal to what? What's result going to be equal to here? To root.val. Cool. This will say basically if this node has them as a descendant, we're going to update it. After updating it, we just want to go further and further down. Solve root.left. Root.left. We gotta make sure we keep track of nodes. If root equals null, return -1. Root.left A, B, solve. Root.right A, B. Sweet. Nice. Good. Wait, which one did I not solve? Is it friggin' Wolf of Wall Street? No, it's beer bottles. Stupid beer bottles. Stupid beer bottles. Okay, let's solve beer bottles as much as I don't want to. Okay, let's just... while n is greater than or equal to 0. Okay, so int exchanged. So if n greater than or equal to, if n is greater than equal to 3, I'm gonna do this, right? We're gonna say drink plus equals 3, n exactly 50%. Wow. So n minus equals 3 minus equals 3 minus equals 2 okay, because we drank 3 and we exchanged them for 1. Drank plus equals n equals 0. Return drink. Dumb, very dumb question. Assuming it's like a math formula I have to just plug it into. Okay, so answer plus equals n, because we're gonna drink all n. Available is n over 3. Yeah. Left. Okay. Which one's this? This is the... Oh, right, I forgot this is... It's using like actual pointers and not just like object references. Wait, this is the last question. Okay, so I'm glad I wasn't the only one who needed a helper method for this. What is okay, this is just a max function. Yeah, okay. Great, okay. Got 15 minutes left. Let's go ahead and jump over to the Microsoft LeetCode tab. And I think I'll do one more and then I'm probably out for the day. At least for now. My brain is at the point where it's sort of starting to get fried. That's another rejection letter from a company. That's fun. I decided to not move forward with the interviews. Wait, really? Oh, cool. Okay. Well, that's another rejection down the line. It's okay. We're gonna be fine. Gonna get a job. Gonna land Microsoft tomorrow. Gonna do it. Minimum deletions to make character frequencies unique. Freaking LRU cache. Okay. I've heard a lot about LRU cache. I've heard it's overused and it sucks. Do I want to try and tackle LRU cache? Because I mean, if you look at the frequency here, right? I did, what was it? Like longest happy string yesterday. Longest happy string I can pretty confidently solve if it comes up because I know the trick to it now. Reversing words in a string, minimum character deletions don't feel like that. Count good nodes in a binary tree. Least frequent, oh, LFU cache. See, because LRU cache, from my understanding, right, it shows up often enough, I'll just do it. LRU cache, it is entirely dependent on utilizing the correct data structure. Now I'm kind of curious, right? Is LFU cache on LeetCode? I want to see what the... yes. LFU cache. Should invalidate the least frequently used cache. Because this seems like you're just swapping out, instead of being ordered. Jeez, that word is so hard to pronounce. You need to somehow, some way, keep track of... Okay, real quick, I'm curious about the data structure. There's no solution. Okay, I just want to see the data structure. Doing this and oh. Right, because does it all have to be an O of 1? Yeah, it's a DLL as well. Goodness. Yeah, no. See, this is why I don't solve hard questions, because I mean, okay, reasonably, if I've seen and solved like LFU cache, I still think that I would I'd still have trouble with it. Because I know for this one I need DLL and a map as well, but my brain's at the point where, I mean, I've been at this for almost 2 hours, solved 2 sessions here. It's more poorly written than it should have been. Okay, let's see what we can do with LRU cache here. Because pretty much LRU cache was a medium, but then from my understanding it got so overused that it is no longer considered a medium. It's like labeled as medium, but it's considered easy because of how often LRU cache is really used. Okay. Initialize the LRU cache with positive size capacity. Return the value of the key. The key exists, otherwise return 1. Update the value of the key if the key exists, otherwise add the key value pair to the cache. If the number of keys exceeds the capacity from this operation, evict the least recently used key. Obviously we need the hash map, right? Hash map of integer, okay, then int capacity. I'm going to move this instantiation over. Capacity equals capacity. So DLL removal. What is the runtime of DLL removal? Like if I want to DLL runtime. So I don't actually think I need to write my own DLL here. Maybe I do. Because I need to be able to shuffle things. A double-ended queue could do the trick. However, you can't remove things from the middle of a double-ended queue like you would need to here. So I think it is... I think it is constant time, technically, to move items around in a DLL. So let's go ahead and write a really basic... How do you write an inner class in Java? It's been a while. Okay. Class outer, class inner. Okay, cool. First of all, let's do this, right? Class DLL node equals new DLL node public DLL node int val. And DLL node means a previous and a next, right? Next. Int val. Goodness, this is where the trouble becomes. I haven't written a linked list class in a long time. Okay, we got 10 minutes here. I think after that finishes, I'm gonna, there's no inbuilt DLL in Java. That's a great question. Does Java have a built-in double linked list? Huh. Okay, good catch. I don't know why I decided the first thing was to build it from scratch. Add. Shows the end element at that specific. Okay, so guess the issue is doing this in O of 1 time. How the heck do we, because we need to find the item in the linked list. And then let's make that linked list, I guess. Cache. Okay, how are we going to do this? How do we, in O of 1, find something in a doubly linked list? Because moving it around might be fast, but finding it is the issue. Provided you know the location. That's what I'm thinking here. Initialize the LRU cache with positive capacity. Return the value of the key if the key exists. Do I need to, like, store its current position in the DLL? That might be it. I might need to do, like, a dumb thing like this. Cool, okay. Because I think maybe doing it this way. Let's make sure this compiles first and foremost. Cool. Make sure it compiles. Doesn't like that because I forgot to close the second bracket. There you go. Forgot to close it again. Okay. Compile, please. The trick in these O of 1 questions is to use as much memory as possible, storing and caching everything in O of 1. Yeah, see, it's very, I guess, counterintuitive for me to try and, I'm always trying to minimize space complexity, but in the O of 1 questions, I guess seeing, hey, run this at this speed, like at O of 1, should always be like, hey, let's sack as much memory as we need to then be able to get a faster runtime. Because memory's cheap, computation power is more expensive. This dot capacity. Wrong answer. All right, that's easy. Okay. But do we not have to update? Okay. So, first of all, let's do a get. Get should be easy. We return okay, so this one is easy. If map dot contains key, this key, but don't we have to shift? Actually, no, we really don't have to shift it. We do. You know what? I'll get to that when I get to that. Return map.get key.get 0. We will allow our list to be value index. There you go. So that should take care of the get method here. Then put is the one that's okay. So first of all, if map.size less than capacity, we're good. We just want to add it in. we're going to do map.put list integer temp equals new array list. And then we're going to do list.add a value of value. Now we need to figure out where exactly its index is in our DLL. Find index in DLL. So we want to add it, and adding it puts it... Oh goodness, why are DLLs so hard to visualize for me? So we want all the new stuff to go ahead. So the smallest index, which is going to be the back, is going to be what's getting removed from. And the things that are at the front are going to be left. So list.add cache.size. Is it cache.size? Yeah, I'm not really sure, man. This question is... It came up a little too late in the session for me to comfortably, like, tackle it. Okay. So... the issue here is that when we remove something, all our indices in the map then become in... Actually, no, they don't. They do? No, they don't. They don't. Oh, goodness. This is like... It's... Okay, here's what I'm thinking. We don't need to, like, actively actually remove anything from the cache. In the map, you retrieve its old location, remove that location from the DLL, and add new location in the front, and save that location. Yeah, but doesn't that change where things are in the DLL? Because, for example, the reason that I'm sort of cracking my head here is, let's say we have 1, 2, 3, 4, 5. I go and let's say these have values of, 2, 5, I don't know, 1, and 8. If I go in and I remove this element, does everything else not shift back by 1? And are my location indices then inaccurate? Because it's okay for things that were before it, but all of these here are now invalid. Because I'll try and access, let's say, index 3 or index 4 where I was expecting a 1 to be, but now the 8's there and I'll remove the wrong element. That's the part that's confusing me. I feel like I'm so close, but I just can't. Goodness, and on my luck, I'm gonna see LRU cache. Sweet, okay. Let's go ahead and I guess go over our solutions for these ones, and then we'll figure something out for the LRU cache. So, time space complexity, okay. Wolf of Wall Street, what I did here, initially my solution was n squared, which was terribly slow. It TLE'd, I was trying to basically check from every point what's the maximum amount of profit that we can get. It's very slow, very inefficient, space efficient, but not time efficient. The solution that I ended up with was to go through the array. I do see the message, I'll come back to that once I finish explaining this one. So, we basically start here, and going up through the array, we find every time we find an element that's smaller than our current minimum, we update it. We keep doing that until we get an array of the smallest element as we progress through the array. Then we do the same from the right side, looking for the maximum element. And because we have the max and the min for that location, we know that what the absolute max profit we can get is for that location. And that's what we're doing right here. And then we just return the max profit. This runs in n space and n time. Technically 2n space because we are using 2 arrays, but it just gets boiled down to O of n. Pretty good solution. Beer bottles, this question sucks. I know I did it very slowly. It's like a terribly slow solution, but all I basically did was pretty much, if we have more than 3 bottles left, at this step, let's drink 3, but subtract 2 because we can trade those 3 bottles in for 1. O of n, it's a good question on time complexity. I don't actually know the time complexity of this is, to be honest. Largest tree sum path. This was a very interesting question to tackle. I quite enjoyed it. It's a very good refresher on working with finding sort of paths in trees. The one thing I realized a couple days before my Google final was that post-order traversals are your best friend when it comes to needing to do bottom-up recursion. Pre-order and whatever the other one is, pre, post, and in, I think in order. Yeah, in order is left, right, left, middle, right. Post order is left, right, middle, and pre-order is middle, left, right. So the reason that this is great is because it allows you to evaluate the subtrees before you actually look at your current node. So what I did in this one was pretty much a post-order traversal, and at every level, because I'm doing it bottom up, I would at every level have the biggest sum that we can achieve from its left subtree and its right subtree. So the helper method here does just that. If we find a null node, its value is inherently 0. We check left and right with this, and we sum up, pretty much find left and right here finds us the biggest paths that we can have. Then the max, a little bit cheated here, but I mean, I think it's okay. Pretty much is the max that we have currently bigger than the path from the left subtree here, the right subtree through this, pretty much updating the max path. And then we want to pass up the max path that we found, which was either our, let's say here, left path or right path, plus this current node, so that this node up here has the path to this node, and then whatever was the max before it. And that allows us to sort of bottom up recursively calculate at every level the max path. Runtime is O of n because we're only really hitting every node once. Space complexity would be O of 1 from what I understand. So yeah, pretty interesting question, quite enjoyed that one. Lowest common ancestor really gave me a run for my money because I didn't know how to do double searches. But quite literally what I did was like, hey, I can't search for 2 elements at once, so I'll just search for 1 element 2 times. So I wrote a search method which allows me to basically check a given subtree for the contents of a node. Once doing that, if we find that node anywhere, we return true. And because this time we want the lowest node, a bottom-up recursive strategy would not work because let's say we have one here that has it, but the one above it would also have it, and we'd inherently end up updating that one. So we want to go top to bottom, meaning we want to check the root node, then check the ones below it, below it, below it, which is why we're doing a pre-order traversal here rather than a post-order traversal. So pre-order, we check the root, and we go and try and solve the left and the right. This will always allow us to get the lowest node that has the 2 ones that we're looking for as its children. And the condition we're saying is if the subtree for root contains A and the subtree for root contains B, we know that this node itself has those 2 as its children. So we go ahead and do that. I think what could possibly make it even faster here is potentially moving this into here. Because if it doesn't have, if the root node itself that we're looking at doesn't have those 2 things we're searching for as its children, there's no point to really even search further. So we only keep searching down the path that we know contains those 2 nodes. Runtime, I think, is... it's going to be like n times n, maybe like n squared, n cubed, somewhere there. Okay. LRU cache. Suppose you have 4 elements currently in the map. 1, 2, 3, 4. Their locations are location 1, 2, 3, and 4. Suppose you access 2, you remove it, and then add loc 2 to the front, so you get... Wait, hold on. Oh my goodness, they're nodes. You're holding pointers, not indices. You're holding pointers, not indices. That's what that is. Okay. That's why a list doesn't work, but a linked list works, because here it's not a list, it's a list of nodes. And your map needs to store a how do you store an individual node from a linked list? How do you store that reference? That's what I'm thinking. Okay. How do we .get, what's the .get method? Goodness, am I thinking of this wrong? Where's .get? Returns the elements, but this will return an integer. We don't need an integer. There has to be a way to like... See, because I need to hold a pointer. I don't need a list. I need to hold a reference to a node in that DLL. I don't know if this will allow me to do that. Descending iterator contains, removes all elements, add last, add first, offer first, peak, pull, pop, push, remove. Yeah, I don't think I can do that. Because from my understanding, I need to, pretty much, rather than, yeah, I don't think I can do it with a linked list. Okay, I'm gonna look at what other Java solutions say here. Yeah, DLL and hash map. Yeah, see, no, that's why. So I was on the right path, because I don't think you can do it with a DLL, with the built-in DLL. Yeah, okay, so that's what I was stuck on. Here, let's copy this solution. I'm not taking credit for the solutions. It's definitely not mine. But I think the thing that messed me up is trying to use a linked list rather than building out my own DLL. Because, here, let's look at that. Submit it. Cool. The reason that he builds out a node of his own is that with a linked list, you can't get a direct reference to any given node. Even though it is being represented using a doubly linked list, you can't get a reference to any given node. This allows you to do it just that, because the map stores a node. Exactly. And every time we need to get, we get the key, we get the value, perfect. Otherwise, putting, if map contains key, temp get key. So we hold on to the value. Then, so temp previous null, temp.next is equal to head. We move it up. Head.previous equals temp. Yeah, okay. If the map doesn't already contain it, we add it. And then this is where we handle the removal. Yeah, no, honestly, knowing now that it's because you can't really, there is a fix, really. Java does all the overhead. Let's see. Okay. LRU cache capacity. Okay, so linked list and hash map. Okay, so a linked hash map. I have never, here, real quick, I want to look up Java linked hash map. Jeez, I have never once have I actually used this data structure. Okay. Get, so linked hash map contains key. Retrieve val is we get that value. We remove the key and we just put it into the front. So it's a hash map but it's also a linked list because it keeps... Okay. That's so sick. That's such a cool solution. Hold on. So if it contains the key, then we remove the key. Else... This one I'm a little confused about as to why we're just removing the key. Oh, so if it contains it, we remove it. If the size is equal to capacity, first key is entry set iterator next get key. What is entry set? Return a set of the view mappings contained in the map. Okay. Dot iterator. So we iterate over that. So we get a set, we iterate over the set, we get key. Get key. What is get key? So we get, I think, the current dot next dot get key. So we remove it from the map. That's such a clean solution. Oh my goodness. So you would never have known this because generally from all my 3 years now experience working with Java, I've never once heard of a linked hash map. This is really, really nice. I'm gonna make sure to, I'm gonna favorite this tab. It's a very nice, let's go ahead and save that. Wow, okay, this is cool. I've never, so I'm assuming it's a bit bulkier space-wise than a regular hash map, but allowing, this is just an ordered hash map, isn't it? It allows you to do the hashing, but also allows you to keep an inherent order in what you're doing. Very, very cool. Okay, I've been at this for, 2 hours now? My brain's a little bit fried. Solved, 4 in the first session, 4 in the second, 1 in between, and I'll say LRU cache, sure. Wait, no, I think I solved another one after this, so I think 10-ish problems in 2 hours. It's pretty fast, not gonna lie. But I think I'm kind of spent for now. I need to go have breakfast. Writing a DLL from scratch in Java otherwise would have been a headache. I think honestly, not particularly. You don't really need the list aspect of it. You just need a doubly linked node. But the only difference really between using that and a doubly linked node would be the fact that I guess you have to just write in all of your operations. So for example, to remove, you have to manually shift all the references around. But I will take writing that really cool, really clean solution over this one any day. But yeah, I think that's gonna be it from me here. I'm tired, I'm worn out. Gonna go probably have breakfast and continue working on this definitely not rip-off Mega Man game. Yeah, appreciate it. Thank you guys for stopping by. Hopefully everyone learned something today. I definitely learned about a whole new data structure that I now need to look into. Oh, Danny, welcome. First time. Not sure if you came right at the end or you've been just kind of lurking around, but welcome. Always welcome to stop by. I'm going to be gone tomorrow. They really gave me like this time schedule. I think the welcome event that I'm supposed to attend. Hey, thanks for the follow, Danny. Really appreciate it. Yeah, thanks. Appreciate it. Yeah, no, that welcome event starts at 8:20 in the morning. So I have to be up at like probably 7:45 to make sure that I can have time to get ready and be fully awake by that time, hopefully. So, yeah, thank you everyone for stopping by, and I'll see you hopefully Friday. Yeah, I'll be back Friday, so hopefully, Friday. Not sure where you're at in your CS journey, but more than welcome to hop in, more than welcome to join. And yeah, see all of you later.